Right. We'll first discuss how a Vernier caliper is used, how we can take measurements using this instrument. Can one of you tell me what we use a Vernier caliper for? Quickly, you can unmute now. What is a Vernier caliper used for? Okay, I got one response as measuring small lengths. Fine, fine. Okay. So to measure small lengths or distances, we use this instrument. Okay. How small? Usually smaller than what a regular scale, measuring scale can measure. Okay. So suppose there's a measuring scale like this. The reading shown here, 0, 1, 2, 3, so on up to 10, they are in centimeters. Okay, fine. Let's say you want to measure the size of an object or the length of an object using this scale. What will you usually do? You will make sure that one edge of the object coincides with the 0 of the scale, and depending on where the other edge ends up, you can estimate its length. Okay. Now this is a regular measuring scale. You can see divisions on this scale. The numbers 0, 1, 2, 3, they are in centimeters, and each centimeter is divided into 10 smaller parts. Okay. And 1/10 of a centimeter, you know, it is millimeter. So the least count of this measuring scale is 1 mm. Okay. That is the smallest measurement you can take using this instrument, measuring scale. And least count has another meaning also. Least count, as the name suggests, it's the smallest measurement that you can take. The other meaning that it conveys is any length you measure using this instrument will be a multiple of the least count. Okay, so that is also, that is another way in which least count is applied. The total measurement has to be a multiple of the least count of the instrument. Okay, now you all look at this. You can see the SD card placed beside the scale. Assume the left edge is lined up with 0. You use your visual inspection and tell me what is the length of this SD card as shown by this scale. Okay, type your answers in chat. I want answers from all 5 of you. I'll give you 1 minute. Right. So some of you gave the answer as 2.6 centimeters. Another answer I got is 2.7 centimeter. One more answer I got is 26 millimeters. That is 2.6 centimeters. Okay, fine. Fine. And good that you all gave answers only up to that decimal place. Now, assuming the left edge of the SD card is lined up with 0, if you observe this carefully, okay, let me just zoom. I took a screenshot of that. If you observe carefully, the right edge of the SD card coincides with this point on the measuring scale. And this is 2 centimeters plus another 5 millimeters. This is 6 millimeters. So it's between 2.6 and 2.7. Okay. So 2.6 centimeters is definitely less than the length of this memory card, less than 2.7 centimeters. Fine. So we can say that the length is 2.6 centimeters plus something. Now, how much that is cannot be found using this instrument. You may estimate, okay, by visual inspection, you may say that it is about 2.65. It is exactly between 2.6, 2.7. So you may say it is 2.65, 2.66. But those are rough estimates only. The instrument, this measuring scale, doesn't have that division at all. 2.65, 2.66, those divisions are not there. Okay. So I won't say any of you is wrong. Some of you said 2.6, some of you said 2.7. That's fine. It all depends on what it is nearer to. Okay. The way you look at it. I mean, based on the way you look at it. That's okay. So because the least count of this measuring scale is 1 millimeter, that is 0.1 centimeter, you can only say it is either 2.6 or 2.7. You can't give readings like 2.65 or 2.66 or anything like this. Okay. So every instrument has a minimum measurement that you can take using that instrument, and that's what is called the least count. Now, in a vernier caliper, the least count is less than 1 millimeter. So you can measure distances less than 1 millimeter using a vernier caliper. Let's see how it can be done. So the basic idea of a vernier caliper is that it uses two scales. Okay. First scale, the long one that you see on the screen, which has readings from 0 to 5, that is called the main scale of the vernier caliper. And a main scale is just a usual scale. Unless otherwise specified in the problem, the main scale is just a usual scale. Okay, the usual measuring scale that we see. And it's mentioned here also. Each main scale division is 0.1 centimeter, means 1 millimeter. Okay, see this diagram is actually stretched a little bit. So from here to here is 1 centimeter. Okay, from here to here is 1 more centimeter and so on. So these 1, 2, 3 that are written on the main scale are centimeter readings. It looks longer than a centimeter, but assume it is a centimeter. Okay. Now each centimeter is divided into 10 equal parts. So each division, each smallest division you see on the main scale is 1 millimeter. So we say that the main scale division, one main scale division is equal to 1 millimeter. You can call it as 0.1 centimeter also, nothing wrong in that. Okay. So the main scale is a usual scale. Parallel to the main scale, there is another scale called the vernier scale, this one. Now, what is the difference between the main scale and the vernier scale? The divisions, the size of each division. Okay. You can observe it more clearly in this diagram. Now, the vernier scale can be slid on the main scale. When you look at an actual vernier caliper, you'll be able to understand that this scale can be slid over the main scale like this, parallel to it. You can move it around. And you can see the jaws here. This jaw J1 is fixed. The other jaw J2 is movable. It moves along with the vernier scale. Okay, it is rigidly connected to it. Fine. When the two jaws are in contact with each other, I'll show you a simulation also. When the two jaws are exactly in contact with each other, means there's no gap between them at all. What you will see is that the zero of the main scale, okay, the zero division of the main scale exactly coincides with the zero division of the vernier scale. If this happens, then it is a properly designed vernier caliper. Okay. When the jaws are in contact with each other, if the zeros exactly line up with each other, the vernier caliper is properly calibrated or properly designed. You say that it has no zero error. Okay. See, the jaws are in contact with each other means you are not trying to measure anything. Then it is supposed to show zero and it shows zero. Now observe the difference between main scale and the vernier scale. Keep yourself muted, all of you. Okay. Observe the difference between main scale and the vernier scale. On the main scale, we had already discussed, each main scale division is 1 millimeter. But see, when the zero of the main scale is lined up with zero of the vernier scale, the 10th division of the vernier scale lines up with 9 of the main scale. Okay, or in centimeters, 0.9. 0.9 centimeters coincides with 10 units on the vernier scale. Okay. Or just to avoid confusion, let me change these to millimeters itself. This is 5 millimeters, 10 millimeters, 15 millimeters, 20, 25, and so on. So the 10th division of vernier scale will exactly be lined up with the 9th division of the main scale. That means 9 main scale divisions are equal to 10 vernier scale divisions. Now see, this is not a rule that 10 VSD should always be equal to 9 MSD. Vernier calipers can be designed in other ways also. Sometimes 20 vernier scale divisions coincide with 19 main scale divisions. They can change the way the instrument is designed. Okay, but the most commonly available version of the vernier caliper is designed like this. So I'll keep a star here. This can be changed. Fine. Other examples are 19 main scale divisions equal to 20 vernier scale divisions. In fact, they can give you any ratio in the problem. Okay. Now, what does that mean? Each main scale division was 1 millimeter. So 9 times of that is 9 millimeters. 9 millimeters become 10 vernier scale divisions. Okay. For this vernier caliper, what does that mean? Each vernier scale division is 9 by 10, that is 0.9 mm. Okay. So this also depends on how the vernier caliper is designed. It's not the same for all of them. So you have to get that information from the problem. How many main scale divisions are equal to how many vernier scale divisions? They'll mention that in the problem. Okay. Now, how can this instrument with two scales be used to measure distances which are less than 1 mm? Okay, let us understand this carefully. When the zeros are lined up, okay, when the 0 of the main scale is lined up with 0 of the vernier scale, the 9 of the main scale is lined up with 10 on the vernier scale. Okay, let us zoom into that part. Just a moment. Yeah. Observe this carefully. This is most important. If you understand this, you can understand how measurements are taken using a vernier caliper. Now, you know that the vernier scale can slide parallel to the main scale. Okay. So when the jaws are in contact, the zeros will be lined up exactly. And if zeros are lined up, the 9 and 10, 9 of the main scale, okay, I'll call this as 5, 10. 9 on the main scale will line up with 10 on the vernier scale. Right. Now see, each main scale division, this gap is 1 mm. Okay. All the gaps on the main scale are 1 mm each. Next, each vernier scale division, we just calculated that. You need to remember how to calculate that also. Okay. It depends on how many main scale divisions are equal to how many vernier scale divisions. Based on that, you can tell how much is each vernier scale division. For this particular instrument, it is 0.9 mm. Okay. So the gap between the divisions on the vernier scale is only 0.9 mm. Okay. Between any two divisions you take, the gap is only 0.9 mm. Okay. Now the zeros are lined up. 9 will be lined up with 10. 9 on the main scale will be lined up with 10 on the vernier scale. That's fine. Observe carefully. There is a small gap between 1 on the vernier scale and 1 on the main scale. Can any of you tell me how much this gap is? Between the 1 and the 1, how much is the gap? Think carefully, not any of you. I want all of you to answer. Type in chat. I'll give you 1 minute. Okay, let me explain. The gap between 1 on the vernier scale and 1 on the main scale. Okay. This line and this line, the gap between these two is nothing but the difference between a main scale division and a vernier scale division. You subtract that orange length and this green length, you will get the gap between them. Okay. And in this particular case, each main scale division was given to you as 1 mm. And we found out that each vernier scale division is 0.9 millimeters. Therefore, the gap there becomes a main scale division minus a vernier scale division. That is 1 minus 0.9, that is 0.1 millimeter, which is 1/10 of a millimeter. Okay, hope this is clear to all of you. So when the zeros are lined up, the gap between the one on the vernier scale and the one on the main scale will be 0.1 mm. Okay. Now one of you tell me, how much will the gap between the two of the vernier scale and the two of the main scale be? How much will the gap between these two be? Yes, Rishikesh, your answers are correct. Others also think carefully and answer. I'll give you all 1 minute. Right. Those of you who answered, your answers are correct. You gave the answer as 0.2 mm. Makes sense. See, the distance from 0 to the second division on the main scale is two main scale divisions, that is 2 mm. And the distance from 0 to 2 on the vernier scale is two vernier scale divisions. Each vernier scale division is 0.9 mm. Then 2 of that will be 1.8 mm. So 2 mm minus 1.8 mm. The gap between the two of the main scale and the two of the vernier scale will be 0.2 millimeters. Okay. So between 1 and 1, the gap is 0.1 mm. Between 2 and 2, the gap is 0.2 mm, and so on. You can write the sequence. Between 3 of the vernier scale and 3 of the main scale, the gap will be 3 main scale divisions minus 3 vernier scale divisions. So 3 to 3, the gap will be 0.3 mm, and so on. Finally, 9 to 9. Okay, this gap will be 0.9 mm. The gap will go on increasing. Okay. And one more very important thing you need to notice here is that when the zeros are lined up, the 9 of the main scale will be lined up with 10 of the vernier scale. You will see that no other division in between will be exactly lined up with any division of the main scale. That is a very important property. Okay. See, in simple exams like NEET and JEE, they may not trouble you in this much depth, but in exams like advanced and all, they can ask you those kind of questions also. If you want to design a proper vernier caliper, when zeros coincide, only one other division should be coinciding. No other divisions in between should coincide. Okay. We'll discuss one question at the end if time permits. What happens if another coincidence is there in between? But for now, in this particular instrument, no other divisions are coinciding in between except 0, 0 and 9, 10. Okay. So you know that the gap between 1 and 1, one of the vernier scale and one of the main scale is 0.1 mm. Two of the vernier scale, two of the main scale, 0.2 mm and so on. Okay. Now one of you tell me, you can just unmute and tell. If you want to make the one here and the one here coincide, okay, if you want to make them lined up, how much should you shift the vernier scale? Main scale will be held stationary, vernier scale will slide on it, no? How much should you slide the vernier scale to make the one and one get lined up? Yes, Vijay Kalyan, your answers are correct. Whatever is the gap between them, you have to slide them by that much distance. Okay, 0.1 mm, correct. So to make this one and this one line up, you have to shift the vernier scale by 0.1 mm, 1/10 of a millimeter. Okay, good. To make the two here and the two here coincide, you will have to move the vernier scale by 0.2 mm. Then these two will coincide. If you move it by 0.3 mm, the 3 and 3 will coincide. Okay, and so on. That is how a vernier caliper measures distances which are multiples of 0.1 mm. Okay, so if you want to make the one coincide, to make one on the vernier scale coincide with the next division on the main scale, you will have to shift the vernier scale by 0.1 mm. Okay. To make the two coincide, you will have to shift it by 0.2 mm. To make the third division coincide, you will have to shift it by 0.3 mm. That exactly is how a vernier caliper measures distances as small as 0.1 mm and multiples of it. Okay. Now here we can talk about, or we can define the least count of a vernier caliper. In this case, okay, means for a vernier caliper designed like this, where 10 vernier scale divisions coincide with 9 main scale divisions and each main scale division is 1 mm. In this case, the measurements you get are like 0.1, 0.2, 0.3. Therefore, the least count becomes 0.1 mm. Okay. But how exactly did we derive this? We need a least count formula which works in any vernier caliper, not just in this case. No. So can one of you unmute and tell me how we got this 0.1 mm exactly? Like how did we get these numbers 0.1 mm, 0.2 mm and so on? What were they? Suhan, your answer is correct. Basically that 0.1 is the gap between one on the vernier scale and one on the main scale when the zeros are coinciding. Okay. This gap was 0.1. How did we measure that gap? Main scale division 1 mm minus vernier scale division 0.9 mm. By subtracting those, we got 0.1 mm. Okay. That is the actual formula for least count of a vernier caliper. 1 main scale division minus 1 vernier scale division. This is how you can always safely calculate or safely find out the least count of a vernier caliper. See, for the usually available vernier caliper in the market, the least count is 0.1 mm. But that need not always be the case. Okay, let's solve one problem here. Suppose you are told that each main scale division, okay, you may use calculator if you want to solve this problem. Suppose each main scale division is 1 millimeter itself. So the main scale is a usual scale. Okay. And you are told that, fine, 20 vernier scale divisions coincide with 19 main scale divisions. Okay. Derive least count of that vernier caliper. Do this all of you. I'll give you 1 minute. Solve quickly. Okay, let's discuss. See, least count is the difference between a main scale division and a vernier scale division. Main scale division is 1 mm that is given to you in the problem itself. Minus. You have to find out how much is each vernier scale division. And how do you do that? You are told that 20 vernier scale divisions are equal to 19 main scale divisions. Means 20 VSD are equal to 19 MSD. Each MSD is 1 millimeter. Therefore, each vernier scale division becomes 19 by 20 millimeters. Okay, keep it as it is. That's all. And then you can express the least count. 1 minus 19 by 20 is 1 by 20 millimeters, which is 0.05. Some of you gave answers as 0.5. That is wrong. 0.05 millimeter is the least count of this vernier caliper. Okay. So keep in mind that the least count need not always be 0.1 mm. It depends on how the vernier caliper is designed. Okay. It depends on the ratio of number of main scale divisions to number of vernier scale divisions. Okay. And the general formula for least count is 1 MSD minus 1 VSD. It will always work. Okay. So now we know how much is the least count of the instrument. The next thing you need to know is how to actually take measurements using this instrument. Okay. For this, let me use one simulation. Just a moment. Yeah. Are you all able to see the simulation on the screen? Moving vernier caliper. Just answer yes or no. Okay, fine. Now observe carefully. This is the regular vernier caliper itself. The zeros are lined up, and then you can see that the 10th division of the vernier scale, lower side, coincides with 9th division of the main scale. Okay. On the main scale, they are written 0, 0.51. Those are in centimeters. In millimeters, it will be 0, 5 mm, 10 mm, 15 mm, 20 mm. Uh, you know the measurements. Okay. So this vernier caliper has a least count of 0.1 mm itself. This is the usual or the regular Vernier caliper. Least count is 0.1 mm. Now, how do you take measurements using this instrument? Whatever is the object whose length you want to measure. If you want to measure the length of an object, what you do is you slide the jaw. Okay, you slide the vernier scale over the main scale and you fit the object between the two jaws. Okay, I think it can be done here. Just a moment. They have not given the object. Okay, never mind. I'll explain. So whatever is the object whose length you want to measure, you separate the jaws and you fit the object between the jaws. Okay, so let me. Okay, fine. Let me take this as an example. Right. So let's say we are trying to measure the length of an object. Usually, I think in your 11th or 12th class experiment, you will be given the bob of a simple pendulum and asked to measure its diameter, or maybe some cylindrical object and asked to measure its length and diameter and then calculate its volume. Okay, I mean, they can ask you to measure anything, not an issue. Now see, when there was nothing between the jaws, the zero of the vernier scale was exactly lined up with zero of the main scale. Okay, you can take a look at it. It was like this. Okay, or even better, you can use this. Just a moment. Fine. The zeros are lined up. When you try to fit something between the jaws, you will move the vernier scale away. Then the vernier zero will move forward. Okay. Now, when we try to measure the length of this cylinder, we see that the vernier scale moves forward by some distance. Again, let me adjust these. This is 5 mm, 10 mm, 15 mm, 20 mm, and so on. 25. These are in millimeters, main scale. Okay. Now, one of you tell me roughly how much distance has the vernier scale moved? Earlier, its zero was here. Okay, when the jaws are in contact, its zero was here. Now, when you place the object between the jaws, its zero has moved forward. Roughly how much distance has it moved? Type your answers, all of you. I'll give you 1 minute. Make it fast. Okay. It can be seen clearly from the diagram that the zero of the vernier scale has just crossed 16 of the main scale. Okay, I don't know why some of you gave answers as 15. It has crossed the 16th division of the main scale. Okay, what does that mean? It means that the length of the object that you are trying to measure is 16 millimeters plus some extra distance. Is this clear to all of you? If you have any doubt, you can unmute and ask. Uh, those of you who said 15, I know why you, I mean, I can understand why you gave the answer as 15. You must have been looking at this edge. Okay, you probably were looking at this edge. See, when the jaws are in contact, it's not the edge that lines up with zero. It's the zero that lines up with the zero. Okay, the zero division and zero division will be lined up. Okay, some of you are giving answers also for the exact length. Wait for a while. Okay, you can observe this diagram carefully. It is not this edge of the jaw which is lined up with zero. Okay, it's the zeroth division and the zeroth division which are lined up. So you have to see how the division, zero division is moving, not the edge of the jaw or some other reference. Okay, so that way if you look at it, the zero of the vernier scale has just crossed 16 on the main scale. Okay, it has not crossed 17. So the length of the object that you are trying to measure should be 16 millimeters plus some extra distance. Okay, just a moment. I'll ask you a few more questions. Now consider this, all of you. Suppose, okay, I think this is clear enough. Okay. Suppose the zero of the Vernier scale is lined up exactly, okay, zero of the Vernier scale is exactly lined up with 16 of the main scale. Okay. You see the other divisions. The 1 will not line up with 17. 2 will not line up with 18. 3 will not line up with 19. 4 will not line up with 20. Other divisions will not be lined up except the last one again. Okay. The 10th division here is lined up with 2.5. That will happen anyway because 10 Vernier scale divisions are equal to 9 main scale divisions. So if the 0 coincides, then the 10th division will definitely coincide. In between, there will not be any other coincidence. Observe that carefully. This is very important. This is how you actually take measurements using this instrument. Okay. Suppose the 0 is lined up with 16. I want answers from all of you. How much will be the gap between the 1 of the Vernier scale and 17 of the main scale? Okay. This is 1 of the Vernier scale. This is 17 of the main scale. You know they are not exactly lined up. How much is the separation between them? Vijay Kalyan, Rishikeshwar, your answers are correct. Others also send in your answers quickly. And it will be better if you type your answers properly along with the unit. Okay, I got answers from 5 of you. All of you have given the correct answers. Basically, the separation between the 1 of the Vernier scale and 17 of the main scale here is nothing but 1 main scale division minus 1 Vernier scale division. That's all, which is 0.1 mm, or it'll be even better if you call it the least count. Okay, so 1 on the Vernier scale to 17 on the main scale. The gap is 1 least count, that is 0.1 mm. Okay. Similarly, 2 on the Vernier scale to 18 on the main scale. The gap will be 2 least counts. 2 main scale divisions minus 2 Vernier scale divisions. That will be 2 times of least count. That is 0.2 mm. And so on. Okay. Answer this next question. Okay. It's quite obvious actually. When the 0 is lined up with 16, no other division will be lined up except the last one. Okay. Now the 1 and 17, 1 of the Vernier scale and 17 of the main scale, they have a gap of 0.1 mm. 2 of the Vernier scale, 18 of the main scale, they have a gap of 0.2 mm and so on. You know the sequence. Suppose you want to make the 1 here line up with the 17 here. How much further should you shift the Vernier scale? 0.1 mm. Okay. For the 1 to get lined up, you should shift 0.1 mm. For 2 to get lined up, you should shift 0.2 mm. For 3 to get lined up, you should shift 0.3 mm. Okay, and so on. Now, listen to this point very carefully. Whichever division of the Vernier scale lines up with any division of the main scale, that division is called Vernier coincidence. In this particular situation that you see on your screen, the Vernier coincidence is 0. 0 is lined up. Other divisions are not lined up. Okay. But if you shift the Vernier scale a little further, 1 can get lined up, 2 can get lined up, 4 can get lined up, 7 can get lined up. Whichever division, okay, I'll write it here. Of the Vernier scale coincides with any division of the main scale, that division of Vernier scale is called Vernier coincidence. Okay, these terms are important. Or you call it as Vernier scale reading also, VSR. Okay, you can, I mean, they can use any of these terms in the question. Don't get confused. Vernier coincidence or Vernier scale division, or Vernier scale reading is the division of the Vernier scale which coincides with any one of the divisions of the main scale. Now, in this particular situation that I'm showing you, no division is coinciding, like 0 is coinciding, non-zero values are not coinciding. Okay, forget 10. Now, let's come back to this question, okay, where we were actually using the Vernier caliper to measure the length. We so far concluded that the length of this object is 16 millimeter plus some extra distance. How much is that extra distance is what we need to find out now. Okay. How much is the extra distance depends on which division of Vernier scale is coinciding with any division of the main scale. If one is coinciding, the extra distance is 0.1 mm, means one least count. If 2 is coinciding, the extra distance is 0.2 mm, means 2 least counts. If 3 is coinciding, the extra distance is 0.3 mm, means 3 least counts. If some x is coinciding, then it will be x into least count. Okay? Or generally, that extra distance is calculated as Vernier coincidence multiplied with least count. Or generally in books you see it this way, Vernier scale reading multiplied with least count. That is the extra distance. Okay. So here in this particular situation that we were discussing, the 0 of the Vernier scale has crossed 16. This 16 is called main scale reading. Okay. So how do you define main scale reading? The last division on the main scale, which the 0 of the Vernier has just crossed. That is called main scale reading. So in this example, it is 16. Okay. Plus that extra distance. Now I told you how to get that extra distance. Extra distance depends on which division of Vernier scale is coinciding with any division of the main scale. And how is it calculated? Vernier scale reading multiplied with least count. That is in a separate bracket. Now you all observe carefully. If you want, I'll zoom in this picture. Tell me which division of the Vernier scale is coinciding with any one division of the main scale. Let me zoom it. Observe carefully and tell. What is the coincidence here? Varshit, your answer is correct. Rishikesh, your answer is also correct. Okay, it is clear from visual inspection, we can say that 3 is coinciding with 19. Okay, it doesn't matter what it is coinciding with, but 3 is coinciding. So this 3 is called the Vernier scale reading. Okay, let's go back to this situation. Suppose the 0 was in line with 16. The 3 and 19, 3 here and 19 here, would have had a gap of 0.3 mm between them, means 3 least counts between them. Now, if the 3 gets lined up with 19, it means that 0.3 mm is covered. Okay, so 3 least counts ahead. That's all. Therefore, the length of this object becomes 16 mm plus extra distance is 3 times of least count. So the answer will be 16.3 millimeters. In centimeters, if you want, 1.63 mm. That is how a least count can measure distances less than 1 mm in decimals of 1 mm or in fractions of 1 mm. Okay. Is the concept clear to all of you? Did you understand how to take measurements using a Vernier caliper and how we get this formula in the first place? Any doubts you can ask? Based on how much the 0 has moved, you note down the main scale reading first. Okay, what is main scale reading? The last division on the main scale, which the 0 of the Vernier scale has just crossed. Note down the main scale reading. Then how much extra distance it has covered, you need to find out. The extra distance that it covers depends on or can be determined based on which division is lined up. Okay, which division of the Vernier scale is lined up with any division of the main scale. In this case, the third division is lined up. So we take this as Vernier scale reading. And for the third division to get lined up, it should be shifted forward by 3 least counts. So Vernier scale reading multiplied with the least count will give you that extra distance. That is how we take measurements using a Vernier caliper. Okay. So if it's a properly designed Vernier caliper, this is how it works. But sometimes uh, due to physical damage or manufacturing defect, there may be a zero error. Okay. One of you is asking, what is Vernier constant? Okay, good question. Good that you reminded me. Least count itself is called Vernier constant. And this is a common confusion between among students. Vernier constant is the least count itself. It depends on the instrument. Okay. Vernier coincidence is Vernier scale reading. Okay. Depends on the object that you are measuring, or so depends on measurement, you can say. Okay. You have to remember these terms. Right. Yeah. So what I was saying is, due to physical damage or due to manufacturing defects, there may sometimes be a zero error in an instrument. Can one of you tell me what is zero error? Quick. What is zero error? Okay, I got one answer as zero of main scale division coincides with zero of Vernier scale. If 0, 0 coincide, then there is no zero error. If they don't coincide, there is a zero error. Okay. Generally, see, not just for a Vernier caliper, for any instrument. Okay. If the instrument indicates a non-zero measurement when it is supposed to indicate zero, then we say it has a zero error. Fine. And zero error could occur in any instrument. So if an instrument indicates non-zero measurement when it is supposed to indicate zero, we say the instrument has a zero error. Okay. There are two possible cases in this. First case, suppose the measurement is greater than zero when it is supposed to be zero. Fine. So zero measurement is being shown as a positive value. Then we call it as positive zero error. So what happens in this kind of instrument? I'll show you an example also. Zero is being shown as some positive reading. Then some other reading will be shown as greater than that. For example, let's say 0 is being indicated as 0.2 mm. Then 5 mm will be indicated as 5.2 mm. It will always show you a reading which is greater than the actual value. Okay. So how do you make correction for it? You will have to subtract the error. If error is positive, correction will be negative. So suppose the instrument indicates 5.2 mm. What is the correct length? Corrected length will be indicated length minus zero error. Okay. If zero itself is being shown as something greater than zero, every other measurement will be shown as something greater. But if you want to correct it, you will have to subtract it and make it smaller. Okay. And the other case, I think it is self-explanatory. If the length is indicated as less than zero, when it is supposed to be zero, then we say it has negative zero error. See, you use the same idea in screw gauge also, any instrument. Okay. So suppose the measurement is indicated less than zero when it is supposed to be zero. For example, let's say the correct length is say 7 mm. Okay, let's take 0 itself first. 0 is indicated as, let's say, minus 0.2 mm. Okay. Then if correct length is 7 mm, it will be indicated as 6.8 mm. So how do you make the correction? How do you get the correct length based on indicated length? You will have to add the 0 error. Okay. I mean, you'll have to add 0.2 mm to it. If error is negative, correction will be positive. Okay. Fine. Now let's see how to find out how much 0 error a vernier caliper has. Consider this example, all of you. It's the same vernier caliper we are still using. Each main scale division is 1 mm and least count is 0.1 mm. But when the jaws are in contact, this is how the situation is. Okay. So you can see what is happening here. J1, J2, the jaws are in contact, but the 0 of the main scale is not lined up with 0 of the vernier scale. Vernier 0 is ahead. Okay. One of you first tell me what kind of 0 error is this? Definitely there is a 0 error. The zeros are not lined up means there is an error. Okay. Is the 0 error positive or negative? Is it indicating measurement more than 0 or less than 0? Rishikesh, Varshit, Suhani, Yash, your answers are correct. Okay, almost all of you have said that it is a positive 0 error. Good. Okay, because the 0 of the vernier scale is ahead. Means it is indicating a positive measurement when it is supposed to indicate 0 measurement. So this is a case of positive 0 error. Okay. Then any measurement you take using this instrument will have an error. Means it always shows an indication. I mean, the length indicated by this instrument will always be greater than the correct length. Okay. But you will be interested in the correct length, no? So suppose you take some measurement using this instrument, how will you correct for it? You'll have to subtract the 0 error. For that, you need to first know how much is the 0 error. Now, what is 0 error? The measurement that it shows when it's supposed to show 0. Now here the jaws are in contact. It's supposed to show 0. One of you observe carefully, not one of you, all of you observe carefully and tell me what is the length indicated by the instrument in this situation. How much is the length that it indicates? I'll give you all a minute. Think carefully and answer. I repeat, each main scale division is 1 mm and least count of this instrument is 0.1 mm. Okay, based on that you tell. Okay. See, the zeros are not lined up here. Had the zeros been exactly lined up, yeah, the situation would have been like this. Had the zeros been lined up, the one on the vernier scale and one on the main scale will have a gap of 0.1 mm between them. Means one least count gap will be there. The two on the main scale, two on the vernier scale, they'll have a gap of two least counts between them. 3 here and 3 here will have a gap of 3 least counts. 4 and 4 will have a gap of 4 least counts. And so on. Okay. Now, for the 1 and 1 to be lined up, it has to shift forward by 0.1 mm, one least count. For the 2 to get lined up, it has to shift forward by 2 least counts. For the 3 to get lined up, 3 least counts and so on. That is how you are supposed to think. Okay. Don't blindly go by the formula. Okay. Now what is happening here? When the jaws are in contact, the zeros are not lined up. You can clearly see that the 1 has gone ahead of the 1, 2 has gone ahead of the 2, 3 has gone ahead of the 3, but the 4 and 4 are lined up. What does that mean? What does that indicate? How much has the scale shifted forward? 4 least counts. For the fourth division to get lined up, it has to shift forward by 4 least counts. Therefore, the 0 error in this case is plus 4 least counts. That is 0.4 mm. So any reading you take using this Vernier caliper, you will always get an extra length of 0.4 mm. Then how do you correct for it? You subtract 0.4 mm from the reading that you obtain. Okay. The fourth division of Vernier scale is coinciding. Means it was shifted forward by 4 least counts. Okay. That is how you determine the zero error of a Vernier caliper. Hope this is clear to all of you. If you have any doubts, you can ask. I'll give you another case also where the zero is to the left side. Okay, and this will be an interesting case. Think carefully and answer, all of you. I want you all to just calculate the zero error of this Vernier caliper. Okay. Each main scale division is still 1 mm itself. Okay, that is not changed. Least count is still 0.1 mm itself. In this case, I want you to find out the zero error. Okay, now one of you is asking, will we not subtract the positive error? Yes, if zero error is positive, you'll have to subtract. That's what I was saying. No, any length you measure will be greater than the actual length. So to get it to the actual length, you'll have to subtract 0.4. If error is positive, correction will be negative. Okay, try this, all of you. Just tell me how much is the zero error in this case. I'll give you all 2 minutes. I got two answers as 0.6 mm and another answer I got is 6 least counts. Why have you given positive answers? You know that the zero is on the left side. No, it has to be a negative zero error. Why did you give positive answers? Anyway, maybe you want to say that it is minus 0.6 mm. Rishikeshwar, Monica, you also gave positive answer. Put the minus sign. Okay. Right. Listen carefully. As I said, this is slightly tricky. Now, clearly, the zero of the Vernier scale is to the left of the zero of the main scale. Means it is indicating a measurement less than zero. An actual measurement of zero is being indicated as less than zero. So this is a negative zero error, case of negative zero error. Okay. How much is the negative zero error is what we want. Now, those of you who said 0.6 mm, I understand your logic. The sixth division is coinciding, so you said 6 times of least count. But that is wrong. Okay. Now, let us go back to that basic diagram where the zeros are coinciding. You have to keep this in mind. Okay, let me clear all this. So basically what is happening here, this is 5 on the main scale, that is 5 mm. This is 9 mm on the main scale. Okay, the common Vernier caliper is what we are considering. Suppose the zeros are lined up. Then you know that the 9th of the main scale will be lined up with 10th of the Vernier scale in this device. Okay, which division exactly coincides? They will tell you in the question. How many main scale divisions are equal to how many Vernier scale divisions? We had discussed this already. Okay. Now, imagine shifting the Vernier scale to the left side. One of you tell me, how much is the gap between these two divisions? They are not lined up. How much is the gap between them?
0.1 mm, sir.
0.1 mm, correct. Okay. Because each main scale division is 1 mm, means from here to here is 1 mm. The orange arrow that I have drawn is 1 mm long. Each Vernier scale division is only 0.9 mm. So the gap between those two divisions is 0.1 mm. So the 9 of the Vernier scale and the division before it on the main scale, they now have a gap of 0.1 mm. Similarly, the 8 of the Vernier scale and the previous division on the main scale, they will have a gap of 0.2 mm. Okay. And then The 7 of the vernier scale and the previous marking on the main scale, they will have a gap of 0.3 mm. The 6 of the vernier scale and the previous division of the main scale, they will have a gap of 0.4 mm. Fine. Now you can tell by what distance it has been shifted back. For the 6 to get lined up with the 5th division of the main scale, it should be moved back by 0.4 mm. And that is what happens in this question that was given to you. Okay. This vernier scale is kind of pushed back, right? The 6 of the vernier scale is coinciding with some division of the main scale. So when it is pushed back, you have to see these gaps. One gap. Okay, wait. The 10 would have been lined up here anyway. So this is the first one. This is the second one. This is the third one. This is the fourth one. It has been shifted backward by 4 gaps. So how much distance has it been moved back? 4 least counts. Therefore, the zero error in this case is minus 4 least counts. It is minus 0.4 mm. Now, how do you say, what does this mean? Okay. What is zero error? A measurement which is supposed to be indicated as 0, if it is not indicated as 0, we say it has a 0 error. And whatever is the measurement it is showing, that itself is the 0 error. Now, how do we say that this device is showing a measurement of minus 0.4? 6 is coinciding. How can we say it is showing minus 0.4? Logically, we understood that it should be shifted back by 4 steps. So it is shifted by 0.4 mm. Okay. Now, how do we generally take measurements using a vernier caliper? Main scale reading plus vernier scale reading multiplied with the least count. Okay. How much is the main scale reading, or how do you identify a main scale reading? Main scale reading, as we had already discussed, it's the last division on the main scale which the zero of the vernier has crossed. Okay, it should be on the right side. Now here, the zero of the vernier is to the left of zero of the main scale. You can say it is to the right of minus 1. Okay, this is 5th division, this is 10th division. This is minus 1. You can say the zero of the main scale is to the right of minus 1 of the vernier scale. Therefore, wait, what did I say? No, I have to rephrase that. The zero of the vernier scale is to the right of minus 1 of the main scale. So it's like it has just crossed minus 1 on the main scale coming from that side. So the main scale reading here is minus 1 millimeter. And vernier scale reading is just vernier coincidence. 6, least count is 0.1. Minus 1 plus 0.6, the answer becomes minus 0.4 mm. So when the zero of the vernier scale is to the left of the zero of the main scale, this is how you are supposed to measure the length. Okay, there are 2 ways of doing it. You can find out by how many steps it was shifted back. Or you can do it this way. Take main scale reading as minus 1, vernier scale reading as whichever division is coinciding, and then get the length. Okay, so the correct answer here, the length being indicated by this instrument is minus 0.4 mm. The zero error here is minus 0.4. Okay, so any measurement you take using this vernier caliper will be lesser by 0.4 mm. So how do you make it correct? You have to add 0.4. So if the error is negative, the correction will be positive. Okay, that's how you identify zero error in a vernier caliper and make corrections for it. Okay, any doubts, any of you? Fine, you can ask me later also. Let us move on to the next instrument, screw gauge.